first, we just wanted to welcome everybody out. So thanks for coming and joining us today. I'll go through the agenda real quick and then we'll get started with our presentation. So first, I'll just give a quick intro on our speaker and special guest, and then we'll go through the presentation, and at the end, we'll have some time for questions. Also, just wanted to make a note that this webinar is being recorded, and we will send it out to everyone afterwards. So be sure to look out for that. So a little bit about our speaker. Judd is a product manager for ASI Automotive. He has worked in EHS, LMS, CMS, logistics, private, public, government, and military spaces. He has built enterprise solutions, formed teams, and developed sustainable systems for growth in both products and sales from the ground up. Now at ASI Automotive, he is a passionate missionary for safety, efficiency, and repeatable testing results using robotic test drivers for ADAS, AV, durability, misuse, and impact groups. And then today we're lucky we have a special guest, Steve Pichota, who is the founder and president of Remote Tracking Systems. RTS provides end-to-end traffic management solutions for proving grounds with browser user interface. Key features include automatic access control, redundant servers, data recording and playback, driver behavior monitoring, and in-vehicle warnings and alerting using RTS-designed GPS tracking and display units with 4G or radio communication modules. The RTS ecosystem for proving grounds also includes weather stations, barrier control, and cameras slew to queue. So we're super excited to have him with us today, and I'll go ahead and turn the time over to them now.
All right, thanks, Brooke. And Steve, thanks for being here. I know we've had a long working relationship between ASI and RTS, and so we're very grateful to have you on the webinar today.
Thanks.
All right, so we're going to jump in. Back in 2017, Alyssa did a study and published some results on this. And we're going to see if things have slowed down or progressed from what she found back in 2017. But back then, she was doing research and found that the testing and validation of the new vehicles, and especially ADAS, was in the very beginning stages. And in the conclusion, she makes that to meet the evolving needs of autonomous vehicle testing, a shift towards automated testing at proving grounds is essential. This shift should concentrate on data and equipment-related considerations to streamline the testing processes. And that's what we've noticed, the challenges at the proving grounds. How do you maintain a safe work environment while the demands on the testing continues to increase? You've got expanding vehicle functions. The rise of the vehicle functions extends beyond collision prevention, and the complexity of the testing continues to increase. The testing equipment itself becomes more complex, and coordinating the growing array of robotic testing equipment on the proving grounds adds to that complexity. And then keeping the driver safe. Now we have a mixture of robot-driven vehicles and targets, along with human-driven vehicles, personnel, refueling sites, different buildings, adjacent properties, and we need to protect those and the track. And that's where ASI and RTS are part of that solution. With ASI's Mobius and RTS V-Track, with our vehicle automation kit, we're able to help overcome the challenges that OEMs are having with testing on their proving grounds. So what do we need to do? Well, it's always best to start with a plan. At ASI, we've automated 75 different vehicle types in 9 different industries. We've automated more than thousands of vehicles on 6 different continents. We can help with testing the different structural tests or durability tests, mileage accumulation or chassis development, severe maneuvers on all different types of surfaces. And our robots can do that without fatigue. So today we wanted to talk through a checklist. What does it take to get started with using automation on the proving grounds? So some of those requirements are always start with safety. Safety first. Start with a plan and a site assessment. Then determine the appropriate method for your testing and evaluation. How are you going to log the data? What type of data is it? Having a traffic management software and system to help protect the drivers. Having a good GPS and base station with RTK correction and multi-constellation support. Having a radio network for communication and for the vehicles and the robots. Having a command center, a place to operate from. And then, of course, having your vehicle automation kits and robots. So we're going to dive in and evaluate these different components. So starting with safety, start with a safety plan and a site assessment, the overall safety of the environment that you'll be operating in, your equipment and how it will be kept safe, and your operational safety and the maintenance and decommissioning of things. How are you going to keep the drivers safe, the system safe, and protected? When we come out, we have a number of questions that we like to ask before we get started. What are the goals of the organization, and are employees motivated, or what are their motivators and their primary objectives? How big is the vehicle? We've worked in a number of spaces. Some of those vehicles get very large. Some of them are very small. Do you have capacity to work within those? How fast is the vehicle going to move? How wide are the roads and the paths? What are the interactions between people and the equipment? When it's moving, when it's not moving? What functions does the vehicle perform near other people or equipment? How close is infrastructure and other buildings? Is there access that can be restricted, or do we need to track people going in and out of the areas? What measures have you taken to keep people safe and to keep people out of the vehicle's work areas? Does the vehicle transport other things or hazardous materials? What types of environments will the vehicle operate in? Are there places that it would lose traction? And what type of incident reporting procedures do you have in place? So some questions there to think through on the assessment. When you're thinking about the testing and the plans, suggestion from the Federal Highway Administration is, what are the test scenario definitions? Collectively define the test scenarios by describing your assumptions and the roles, and what is the definition for success? How are you going to test and evaluate? Are you going to use simulation, a controlled environment, public road testing, a combination of all of those methods? I know AVL has a great solution with their driving cube. And I know other solutions where you're out on the proving ground and you can inject other virtual objects into that. Data definitions, what type of data and how are you going to be able to store that data, and what are the formats that you will be using and translating? And then the test success. What are your KPIs? Is it technical? Is it organizational? Is it working towards public perception? For the data logging, look at standardized data formats and the data analysis. Are you going to use open standards or proprietary standards? In this example here from the Federal Highway Administration, they have 3 different data sources from the vehicle itself and a GNSS location. How is that stored? How are you going to collect the data? From the world objects, do you have barrels or cones, and do those need to be in a specific surveyed location? Do you have lines that need to be drawn on your lanes? What kind of environmental aspects do you have? Are there climatic considerations that need to be accounted for? And do you have tracking systems to log that? And all of these things kind of build up, and then we transition into our worlds. And Steve, this type of data logging that we're talking about here is quite different from the data that our systems track, isn't it?
Yes, Jed, it is. Thank you. So the data that we're talking about is used for monitoring the vehicles, not actually running the test. So it's agnostic to the test, independent of it completely. And when we take that data in to our system, which is a traffic management system, we're able to create a safe environment for the drivers and the vehicles. Now, there's two real components to the traffic management system, or the TMS. We've got the real-time GPS tracking units, as well as a rich set of geofences to make all of the decisions. So what ends up happening is these trackers, which could be either radio-based or cellular-based, send the system over into the TMS, and the TMS then makes quite a few decisions on that. In addition, we send the data over to the ASI's Mobius system, and they provide the collision avoidance in mixed traffic applications. So where you've got, again, the robots in the same location of the human-driven vehicles, we send our data over to them, and it creates a very safe environment. What that allows you to do is increase the level of testing so that you don't have to have an isolated area for robots. So one of the goals of the TMS is, again, increase the amount of testing that can go on in a safe manner. And so combining all of our geofences and all of our rules that we have with the real-time trackers, then we can create this environment. Now, in addition, you can increase the automation at the proving ground, because with all of the geofences you've created, you now have a way to do real-time alerts where operators get notified. You can also notify the drivers that they're doing something wrong. Say you've got a wrong direction or a road that changes direction on a daily basis. The driver may forget which direction it is. We can send them an alert and let them know they're going the wrong direction. Or if they're going to the wrong zone or track, we'll let them know as well. So all this data comes into our system and provides alerting, and we control barriers that way. So it's a complex system of redundant servers based on bookings or reservations. We are able to generate a whole series of reports of how much time on track has been used by each driver, any alerts or overspeed or unsafe driving habits that someone may have. We collect all that data, and we're able to use it to create a much safer environment. So again, the key for us is having a good GPS system. And to go into further detail on that, I'll pass it back to Jed.
Thanks, Steve. And I know this is a big part of keeping our human drivers safe. The human drivers are a very important part on the testing grounds today. And your system allows us to have that mixed fleet, like you said, and also control that access into specific parts of the proving ground when needed to keep the robots and the human drivers separated for certain events. So yeah, and like you said, GPS is a big part of our solution as well. We need a GPS in the vehicles that we use to track where they are, their longitudinal and latitudinal direction. as well as a base station that then plugs into our command and control center. So with that, just some of the basics that we need. Here we've tied in with Trimble BX992, but I know we've got folks from from Genesis on the call as well. And that is something that we would love to be able to integrate with and find a customer that would like us to move in that direction. So what's really important here with the GPS is that it's RTK enabled. It's got at least 60 channels. It's multi-constellation, supports multiple constellations. The output messages that it accepts N-trip corrections, and that it's ruggedized. So the base station is also important, and this needs to have a surveyed position that's not moving, solidly affixed mounted antennas, outputs N-trip corrections, and has an Ethernet connection that is accessible to our command and control software. We also need a communication network. And with that, we do like the Ragent network. They just work. They work well. And what we're looking for from this is at least less than 150 milliseconds of latency, good throughput of at least 50 kilobits per second. The radio must be at least 802.11 capable, and again, be able to connect through Ethernet to our command center. One of the things that we like about the Ragent network is that it uses a kinetic mesh network versus the Wi-Fi based mesh network, which creates multiple redundant connections and strengthens even with the moving vehicles. For the command center, if you're just running with a single vehicle, often you can run on a single machine or even a laptop. Sometimes operators like to have two different monitors, keyboard, a mouse, and that base station e-stop. So we recommend something at least Intel Core i7 or equivalent, at least 32 gigs of RAM, the best graphics processor or graphics card that you can get, and some additional monitors, and then Windows 10 Pro. If you're going to be running more than two vehicles, then we recommend having a Mobius server and separate client. And that server machine needs to be a server quality machine, again with great processor, the octa-core Xeon or better, with at least 64 gigs of RAM, the best graphics card you can get, hard drive space, and Windows 10 Pro. And then for the Mobius client machine, also a decent machine there, or a good machine there with Xeon processor, at least 64 gigs of RAM, and the best graphics card you can get or afford. And then these can be in a fixed command center location or set up as a mobile command center. Often in the fixed command centers, customers will set up cameras along the routes, especially if you don't have a way to see the track so that they can observe the vehicles and ensure the safety of those, if there's any animals or other hazards that wander across those tracks. The mobile command center is nice, where you can take your radio, your GPS base station, those things, and be able to move those around your proving ground to different areas or different tests as needed. Pack those up in a trailer type of a setup. We've got customers that's the way that they have designed to operate. And then they just go out, set up their radio network. They'll have some generators to run any of those radios, and have their server set up in that mobile command center along with their clients and be more mobile in where they operate on their proving grounds. It is also possible from these command centers to teleoperate vehicles where you can remote control individual vehicles as needed. So then, with those things in place, a command center, GPS, the radio communication, you got your safety assessment, you have your success metrics and KPIs, your tests that you're going to do, how the devices to collect the data for your tests. Again, the traffic management and keeping your drivers and other assets safe and protected. Then we're ready to run with robots. Our robots are a collection of sensors, a vehicle control unit, and actuation. It supports testing of different types of vehicles, including cars, trucks, SUVs, vans, buses, commercial vehicles, semis. We have a 12-volt kit and a 24-volt kit. They're designed to go into a very compact location as well as very large trucks. The vehicle automation kit has a roof rack that has the horn, the lights, antenna. If you have a camera, that could be mounted up there. A steering ring that goes on the steering wheel of the vehicle, and pedal and transmission actuation. And then the vehicle control unit that talks with our server. For safety, we've got an e-stop button that we tie in with the RTS system, where we can display the location of the human assets along with the robots. And then we've built in specific programming so that when the robots approach or are approaching a human asset, they will always yield and give way. And you can set up triggers in your vehicles around the DBC CAN messages that perform functions or would bring the vehicle to a stop if needed, or things like that. And then for obstacle detection, you can use cameras, and we also have an integration with the Mobileye camera. And as part of this, what we want is to train our users and customers to grow with our software, grow with our systems on their proving grounds. We know that it takes a lot of infrastructure to get started. So we provide training on how to install the hardware in the vehicles and make sure that the customers feel comfortable and confident with that. And also with the software operation, so that if they need to make tweaks to their tests, that they're capable and able to do that. And then, of course, we provide great support that when you need support, if you want to call us, you can pick up the phone and we have another person on the other line that can help answer your questions. You won't be talking to robots at our facility, you'll be talking to humans. So with all of that, we've consolidated these slides into a checklist. And if you would like this checklist, please reach out to us and we'd be happy to send this along. It's got the requirements for test automation on the proving grounds and those features, those things that we've highlighted during this presentation. And with that, we appreciate you joining us today. Are there any questions?